All right. Howdy, everyone. It's our last class before spring break. Yay. Yeah, right. The bummer with being a student is it really a break? Maybe. I don't know. One day, don't worry, you have a beautiful maybe 9 to 5 with health insurance and things. Anywho. Joke of the day. Let's see. What do you get when you drop a piano down a mine? What do you get when you drop a piano down a mine shaft? A flat minor. Yeah, that's a good one. So, my voice sounds real good. So I posted the practice test I made. So it's there. It's got 22 questions. Your exam will only have 18. So it's not going to have 22 questions. The reason this has 22 questions is I wanted to try to fit enough different types of questions for practice. So specifically, like fluids, like I put 8 questions. And I put 8 questions to try to cover all the different fluid topics. Now in the exam, there will only be maybe 6 or 7 fluid questions. I won't have a fluid question about everything, but you don't know which one I won't include, kind of thing. So, I can only fit so much. I try to cover it all. Anywho, do not use the practice exam as your sole way of studying. It is not enough. If you are only using the practice exam to study, it is not enough to actually make sure you understand it. The practice exam serves as a check of basically, do you understand it? So do not use it as practice. Use it to check whether you understand the stuff. Is my major recommendation. But at the end of the day, you do you. Tomorrow I'll try to make the mixed up problem set, and I'll also make the mixed up top hat questions, and I'll post those. And when we get back from break, we'll do the review day, and then we'll have the exam. You know, all the normal things. So, there's all that. Okay, and I think that's it. Any questions about anything? All right, cool. All right, so fluids. We're gonna finish this, and we'll be done with all the good stuff. So last class, we talked about pressure and all the fun units it has. It has units of pascals and newtons per meter squared and millimeters of mercury. There's other units for pressure like atmosphere and PSI and torrs. We're not going to bother with them, but they exist. 1 atmosphere is the pressure that you are experiencing due to the 1 atmosphere above you. But we're not going to use it, but it's something you might hear at some point. All right, and what was the benefit of pressure? So then we kind of scrolled down to some later point where I said fluids are incompressible. Pressure, any increase in pressure gets experienced everywhere in the fluid instantly. And so what's the benefit of this? Hydraulics was what we mentioned. So you can multiply a force. I can apply a force to one piston and make a way larger force on another piston. 2 things connected by a fluid. So brakes, construction equipment, basically anything where you need a strong force, there's hydraulics. There's this involved. Yeah?
Can you explain why it's a larger force though?
Yeah. So it's the same pressure. The pressure is the same in the fluid. So like if I increase the pressure here, this will increase by the same. And because the pressures are the same, pressure is force over area. So like if you have the same pressures, Awesome. The pressure is equal. Replace those with F over A. And so given some pressure, let's just make it up. Let's say it's 10 Pascal. Well, let's make up some numbers. So let's say you apply a 5 Newton force to a surface area of 1 meter squared. Just simple, nice, easy numbers. Let's say you have another piston with an area of 2 meters squared. And the question is, what force is going to happen there? The second force will be 2, if you just multiply it over. And you get 10 newtons. So it just comes from F over A equals F over A. Now, it's not free. For you to generate this, you would have to first push the first piston twice the distance. So if you push this piston like 2 meters down, the other piston would only move 1 meter up. And if you've ever played with a jack, if you've ever jacked up a car, you got to move that jack all the way down to move the car a tiny little bit. So it's not free energy. Remember, energy work is force times distance. So you get a larger force over a smaller distance. So it's the same amount of work, which is kind of interesting. But generally, when you want large forces, you don't care how quickly you get them. The fact that you can lift a car, you don't care how quickly you can do that. You just need to lift the car. So. Yeah. Did a problem on that. And we said, how do you make pressure? Well, there's a couple ways. So then kind of going backwards. One of the ways is to be inside a container at some depth. Well, I say container. It doesn't need to be a container. And the thing I tried to convey to you all is if I take this beautiful picture and I copy and paste it and I make it skinnier, these two pressures are identical. It doesn't matter how big, how wide your container is. It could be the entire ocean. You only care about how much fluid's above you, which is kind of cool. So I gave you all an example of a straw versus, a pool or something. Yeah. And the pressure at the bottom of the straw was bigger because it was straw. It was taller. There's more fluid above it. You don't care about the left, right. All right. And then what else was there? We talked about Archimedes' principle. And I just started talking about this. This was the last thing I taught you all. So we did a 3x diagram of a water balloon and water. And basically found if it's not moving, something is holding it up. What's holding it up? The buoyant force. How much is the buoyant force? We were able to derive it. Sum of forces equals ma. So if we just kind of write this out, the buoyant force minus the force of gravity is going to equal 0, because if you're not moving, your acceleration is 0. So, ta-da, force of buoyant equals Fg. And ta-da, force of buoyant equals m times g. And that was basically Archimedes' principle, but it's the mass of the fluid, not the mass of the object that gives you the buoyant force. So how much the mass of the fluid you displace times g, that's how much it pushes up. And this is true of any object. Submerged, floating, in between. If you want to know how much water pushes up on an object, how well something's going to float, you just figure out how much of the water you're going to displace, find the mass of that water, multiply it by g, and boom, there's the buoyant force. It's such a simple equation to give you how much water pushes up on stuff. And now we'll do this, and then after this, I'll teach you about apparent mass, and then flow, and then Bernoulli's principle. Again, there's a lot of ideas in this PowerPoint. Fluids is one of those things. There's a bunch of different ideas you got to kind of practice. So. All right, a twin-sized air mattress used for camping has dimensions of 100 centimeter by 200 centimeter by 15 centimeter. The weight of the mattress is 2 kilograms. How much mass could this air mattress hold if it's placed in fresh water and we want to keep the person out of the water? So what's really cool here is all the numbers, these are all real numbers. This is the size of a mattress. This is the mass of a mattress. So if you have an air mattress like this at home, we're going to calculate how much mass you can put on top of it before basically it sinks. And it's based on Archimedes' principle. So, draw a picture. You got your water. Basically, our goal is that our air mattress is going to be, because this is an important visual, the maximum amount that we can place is such that the air mattress is just under, not like under the water, but just like all the air mattresses in the water. If it sinks anymore, whoever's standing on top, it's going to get a little wet. That's the idea here. You could technically fit more on this, but then if that happened, it would sink under the water and wet and whatever. We're assuming this thing's rigid as well, and it's not going to fold in the middle and, a bunch of ideal stuff. So, what are we solving for? How much mass can it hold up? So, I don't even know what we want to call that. Let's just say mass. Mass, hold up. Whatever phrasing you want to use. All right, what's given? I got a bunch of dimensions of an air mattress. If I have 3 different dimensions of it, I'm probably going to find the volume. That's not a big intuitive leap. The volume of the mattress. And even if we don't know why, it's just kind of like this seems like something we're going to do. We're going to convert to meters because centimeters, we always like to convert. So 1 meter times 2 meter times 0.15. That equals something. All right, 0.3 meters cubed. Mass of the mattress equals 2 kilograms. All right, and I want you all to think about how you'd solve this. I'll give you a hint. Forces are involved, so you should probably draw something. If you're not sure, talk to the person next to you. See if they have ideas. All right, so, let's just think through this. How much mass could it hold up? So then we ask ourselves, why is there a limit to how much mass there can hold up? Because as mass increases, the force of gravity is going to increase. As mass goes up, this thing's going to get pulled more and more and more and more down. Can this air mattress hold up an infinite amount of mass? No, there is a limit to the buoyant force that can be exerted. What's the maximum amount? It's when the air mattress is fully underwater. The buoyant force is limited. This is the maximum amount. The more it goes underwater, the more it pushes up. If you've ever played with something in the water, if you try to shove a beach ball underwater, it gets more and more difficult. Why? Well, that's the next question. How do we calculate the buoyant force then? Because that seems to be the idea. It seems to be that, if we do Newton's laws, sum of forces equals ma. Great. The acceleration here is going to be 0. So we have the buoyant force minus the gravitational force must equal 0. That's got to be true. If we then write the buoyant force minus the force of gravity is going to be m times g. But we have 2 objects here. We have the mattress. So the mass of the mattress mass plus the mass of the person times G is going to equal 0. You got, the mattress does matter. It does have 2 kilograms. It's not nothing. So then we're like, okay, so clearly, okay, so I can find this, but I got to find the buoyant force. Okay, how do I find the buoyant force? Like, this is the thought process of going through. It's like, what am I looking for? The mass. Why does the mass matter? And you go from there. You ask yourself those questions. So the buoyant force equals the mass of the fluid displaced. The mass of the, however, if there was water here, how much mass would that water be? That's what that question is. This mass of fluid is, if that mattress wasn't there, there'd be water there. How much water would be there? That's what this mass of fluid represents. And times G. All right. See if you can figure out the mass of the fluid that should be there. That's the next step then. I know G. How much? What's going to be the mass of this displaced fluid? And the punchline there, how do I get the mass of the displaced fluid? Density equals mass over volume. If you rearrange this, you get mass equals density times volume. Do I know the density of water? Yes, it's 1,000 kilograms per meter cubed. Do I know the volume of water displaced? It's the volume of the air mattress. If the air mattress is completely in the water, however much space it takes up is how much space the water would have taken up. So that's the thought process. There's a bunch of like this, then this, then this, then this, then this. And that's really the skill in physics. If you haven't kind of seen it at this point, it's what am I solving for? How does that come into play at all? Like, why does it matter? How do the things I have affect it? And so, yeah, we went down this whole rabbit hole of why does it even matter? Because it affects gravity. Why does that matter? Because you can only lift up so much and so on. So, make a new slide. Chuck this stuff in there. Give myself a little bit more room. But that's all the physics done at this point. Now it's just plugging in numbers. So, step 4. So the buoyant force is going to equal the density of water. I'm just going to chuck that in there. Oh, actually, I'm going to do, yeah, so I'm going to do this in a couple steps. So the buoyant force, this is one of the benefits. So one of the pro things you can do is keep things in variables as long as possible. You'll see why in a second. So now I'm going to take this buoyant force, and I'm going to chuck it in here. So I get that rho times V times G minus mass of mattress plus mass of person times G equals 0. If both terms have G, I don't care. I don't need to plug it in. I saved myself a slight amount of effort. And so, we have the density times the volume minus mass of this. Here, we'll just mass of mattress minus mass of person equals 0. Mass of person equals density of water times the volume minus the mattress. Yay. And that's it. We just plug in numbers. So, mass of the person is going to be 1,000 times 0.3 minus 2. And for once, this is something I feel okay doing in my head. That's 300 minus 2. It's 298 kilograms. And that's how much a twin mattress can hold up. On Earth, 1 kilograms has a corresponding weight of about 2.2 pounds. So this is like 700 pounds. That's a lot. You feel like 700 pounds on a mattress without it sinking too much. Now it's going to bow in the middle and all that jazz, but so there you go. It's a great problem. Like, this is a good problem to get a sense of buoyancy. And yeah, this is every ship you see. The ship has a certain gravitational force pulling it down. Basically, they just need to make sure that the buoyant force, the amount of water they displace, the mass of water that they displace, needs to, times G needs to equal, the G's cancel. Basically, they need the amount of water they displace to equal the mass of the ship. That's the simple math, is how it works out. It needs to be, or I should say, is greater than the mass of the ship. They need to displace more water, more mass of water than the mass of the entire ship. If not, they fail. Boat sinks. All right, there's a couple things following this, couple kind of concepts related to this buoyancy force. So if you go through the motions, you go through math, you get something kind of nifty. And I'm just going to kind of highlight it down here. So this is the major thing that's important. The fraction submerged is just the density of the object over the density of the fluid. It's a really, really nice thing. So if you want to calculate, hey, I put an object in water, it floats. What's the density of my object? You just measure the percentage that's below water and multiply it by the density of water. It's really, really nice and easy calculation. And it just comes from the fraction submerged is the 2 volumes, but you then replace those with mass over densities. But like I just told you all, when something's, you need the mass of the water you're displacing equal to the mass of the object, so it floats and you get this nice relationship. I think it's super handy, so there's a problem on this, but let's just do a quick question on it, because this is kind of one of those conceptual questions I can ask. There's, I think, one of them on the practice test. An object has a mass of 800 kilograms per meter cubed. What fraction of it will be above water? And I'll even take the equation that I just gave you and write it here. Fraction submerged equals density of object over density of H2O. Is the fraction above water 4/5? Is the fraction above water 1/5? Will it sink? Or is the fraction above water 1? Yeah, but another really fun example of this. Have you ever tried to build a boat out of aluminum foil? Like, all you're doing is increasing the volume of water you're displacing. If you crumple the aluminum foil into a small ball, it sinks. Why? Because you don't displace as much volume. If you make it a big boat, you displace more volume, i.e. you displace more mass of fluid, i.e. you increase the buoyant force. The bigger the volume of your object, the bigger the buoyant force. So. All right, I'll give you like 10 more seconds. If you don't know, guess. Have you ever realized this yet? Density of water is 1,000. All right. 5, 4, 3, 2, 1. And these equations work for other fluids. We just keep using water because you're generally not floating things and stuff other than water. All right. So really straightforward. You want to find the fraction submerged. I don't want to write the word again. You do 800 divided by 1,000. Great. That's the fraction submerged. So how much is above water? 1/5. So you got to be careful on these. The amount above water is not the amount submerged, i.e. below water. It seems like a tiny thing, but that's why I underlined the word above. If ever on a test or a quiz or a problem I've underlined a word, it's because there's something significant about it that if you don't take it into account, it's going to go bad. That's often I'll underline to the left or up or right, like stuff like that. Yeah. And it makes sense. If you drew a picture of this, if I had some object with this density that's really close to water, if we said the answer was 1/5 or 4/5, that would mean that this is my picture. That this object that most of it's poking out of water, but it's got a really high density. 800 is really right. So no, it's going to be something like this, where most of it's underwater. Because if it had a density of the same density of water, all of it would be below water. If you had the same density of water, it would just be in the water completely. If I had a density, and we can also see this, if the density of your object is bigger than 1,000, what's your fraction submerged? Some number bigger than 1. Your whole object's underwater. So again, we get that relationship. Density less than 1,000, you float. Density more than 1,000, you sink. Why? Because of Archimedes' principle. That's where that comes from. That's where that rule comes from. This came from Archimedes' principle. This statement right here, mass of fluid equals mass of object, that's the key. That cancels out our mass and life is good. All right. So, now, no matter what, just because something sinks doesn't mean there's not a buoyant force. Just because something sinks doesn't mean the water is not pushing up on it. The water is still pushing up on it. What it means is that the force of gravity is bigger than the buoyant force. If something sinks in the water, gravity's winning. If it doesn't sink, then the buoyant force is winning / tying it out. Why does this matter? So this is something called apparent mass. Apparent mass, if you go in water, you feel like you don't weigh as much. You can pick up heavier things underwater. Why? Because the buoyant force is making them lighter. That's why. The water is helping you. The water is pushing up on it. So, let's just kind of write out, you got some object underwater. It's got a buoyant force up and a force of gravity down. Now the gravity's winning. So, we do force of buoyancy minus force of gravity. And whatever is left over is going to be what I feel. It's going to kind of be how much it pushes down on something. So if we write this out, you get let's call this F net. How do I want to phrase this? Let's call it the apparent force, whatever. It's the leftovers. So the buoyant force is mass of fluid times G minus mass of object times G equals this fake mass. This apparent mass times G. All the G's cancel. And so you get the apparent mass is the mass of the fluid minus the mass of the object. So this picture down here, I think, does the best job of kind of giving an example. I've got some object with some mass. Great, let's make up numbers for it. Let's pretend this thing is 1 kilogram. How do we know it's 1 kilogram? Because we put 1 kilogram on the other side and they equal each other. Great. Then I put it in water. And if you look carefully, there's 2 weights here. And in my picture over here, there's only 1. So let's just say that in water, it only seems to have a mass of 0.2 kilograms. Because I only need 0.2 kilograms here. Why? Because this buoyant force is kind of making it lighter, quote unquote. Mass is not weight. Don't mix up mass and weight. But remember, all these get G's attached to them. Why is this one pulling it down? Because of gravity. Why is this one getting pulled down? Because of gravity. How do we get the buoyant force? It's mass times gravity. It's all gravity. Gravity's everywhere. So you just cancel out all the G's. And so the long and short of this is, in water, it's like things have less mass. How much mass does it seem like they have? Take the original mass of the object minus the mass of the fluid displaced, and that's kind of like how much mass it has. That's what it seems like. You all go in water, you can kind of jump around like on the moon. Yeah, you all can pick up heavy things. This is how you get kind of like that. What it feels like your mass is in water would be the mass of you minus the mass of the water you're displacing. And that would be like your effective mass or apparent mass. So, one use is responding body fat percentage. That's literally the next problem that we're going to do to practice this. So one of the ways you can find body fat percentage is you can submerge someone in water, and you can use this calculation to find their density. Now, it's the density of their entire body when you do this. By knowing the density of their entire body, you roughly know that someone this tall has this much bone in their body, has this much muscle mass, and you can kind of work backwards and get an estimate of how much fat percentage is in their body. Most human, I guess I've heard the statement that big bone's not actually a thing. I don't know. I think people of a certain size, I guess the amount of bone mass in a body is pretty consistent based on height. That'd be my guess. Maybe width. I don't know for sure. So they can do this. This is how they do body fat percentages. They make an estimate of how much. They get the density of a person. They do an estimate of how much of that's going to be due to muscle, organs, bones, and then what's left over is fat. All right, so let's find a woman's density. So in an immersion measurement, she's found to have a mass of 62 kilograms in air. There's no buoyant force, so that's her actual mass. And an apparent mass of 0.085 kilograms and completely submerged in water with lungs empty. So when she's underwater, it's like she's light as feather. She has barely any mass. It's like gravity's barely affecting her because the buoyant force is, pushing her. Great. Then we're just going to go through the steps. What's the mass of the water she displaces, given these numbers? What is her volume, based upon that? Then calculate her density. And then we'll do the same thing, but we'll have our lungs filled with air. And this will be kind of like going back to the first problem we did where we get the density due to other combination of things. So, let's see. We got the mass of the person, 62 kilograms. We have the apparent mass equals 0.085 kilograms. What are we solving for? The mass of the fluid. And this is just a really simple relationship. Now, I don't have this one on the formula sheet. So it might be one, if you're afraid you'll forget it, just kind of put on your note card. Mass apparent equals mass of the object minus mass of the fluid. You just subtract them. It's pretty straightforward. Because why is their mass less? Because they're displacing water and subtract it. So, it's pretty straightforward. 62 equals, 0.085 equals 62 minus the mass of the fluid. So, Mass of the fluid equals 62 minus 0.85. 62 minus 0.085 is 61.915 kilograms. Great. That's the mass of the water she's displacing. That's why she seems to weigh less. She's displacing a lot of water. Makes sense. Your body is mostly water. So if your body is entirely in water, you're basically you can almost imagine your body is just like a water balloon. The amount of water you're displacing basically is your body, because it's as if your body is just water. So, great. What's the density? What's the volume? If ever volume is mentioned, density is mass over volume. Density of water, so, let's just rearrange this. Volume is mass over density. Volume is going to equal my mass of my water divided by the density of water. And you just hop the decimal place a bunch of times. Great. We got the volume of water. Density of water, mass of water, volume of water. All right, step C. What's our density? We're going to use the same equation. But this time we're going to use the person, because that's what we care about. Before it was the water. And just plug in the numbers. The mass of the person is 62. The volume of the person is the volume of the water they displaced. Yeah. Yeah. What do we calculate?
Yeah.
The volume of the person. Yeah, so it's, okay, that's a good point. I kind of rushed through that. The volume of the fluid is going to be the volume of the person. The volume of water they displace is the volume of the person. So this is something you all probably seen before. If you ever want to measure the volume of an object, say you have a beaker filled with water. So this is like a classic experiment. Let's say this beaker originally measures 10 milliliters. If I stick an object in this beaker and the water level rises up to, say, 12 milliliters, what's the volume of my object? 2 milliliters. The amount of volume of water you displace is the exact same as the volume of the object. Because how did that object get underwater? It had to move water. How much water did it have to move? However big the object was. I mean, you could imagine that this thing was just a cube filled with water. That's the amount of water it displayed. So volume is based on space. Yeah, so it turns out that the volume of the fluid is the same as the volume of the person. It's a subtle thing, so I appreciate you stopping me on that. Volume of the fluid, volume of the person, if you're fully submerged, they're the same thing. So yeah, now we get the density of the person. And the density of the person we're going to find is a number bigger than 1,000. Which means they'll sink. Which is something you all are aware of. When you go into water and you breathe out all the air from your lungs, you will sink to the bottom of the pool. Or whatever water you're in. You can change the density of your body. It sounds really weird. All you're doing and so we'll do this in part D now. What if instead she breathes in air? So when you breathe in air, literally all you're doing is increasing the volume of your body. As weird as that sounds, when you breathe in, you're literally just making your body take up more space. Why does that let you float? If you take up more space, you displace more water. If you displace more water, you increase the buoyant force. If you increase the buoyant force, you float. Something you might not have realized. Again, a water bottle, if you empty a water bottle, you've made its volume smaller. And if you empty it enough, it may or may not sink. Plastic's fairly low density, but I'm pretty sure plastic will eventually sink. Whereas if you fill it, if you like blow it up again, you've increased its volume. Literally, the only reason things float is they take up a lot of space. They displace a lot of water. Now, you also want to make sure your gravitational force doesn't increase too much. But, all right. So part D, the last one. Part D, we need to calculate. Copy all this. If her lung capacity is 1.7 liters, will she float? Or, no, not will she. Well, that's the ultimate question. We're going to calculate that they say will she float, which really is a question of what's her density. Whether something floats is just a question of density. So we're going to take the volume of the person, and we're going to add 1.75 liters. Now, right now, we can't do this. Let me rephrase that. 0.0619 meters cubed. I can't just add 1.75 liters to that. They're not the same unit. You need to convert the unit. So this is where I'll remind you all that 1 liter equals 0.001 meter cubed. So we're just going to hop that decimal place 3 times. Boom. So that's going to give you the volume of the volume, new volume. All right, and I'm kind of jumping. So let me actually remind us what we're solving for. We're solving for density. How are we going to solve for density? Mass over volume. And in this case, we're going to have the mass of person plus the mass of the air they breathe in over the volume of the person plus the volume of the air they breathe in. Now, this air does add a little bit of mass, but not enough to really matter. Like, we could calculate the mass of the air if we really wanted to, but I hope that we're going to be okay with saying that the air basically doesn't have any mass. It's air. It's not much of it. Again, you can go through the math and prove this, and you'll find that the mass of air is like 0.000 some numbers. It doesn't really change this answer at all. So for the sake of time, we're going to pretend like it doesn't really matter. It doesn't. All right, so great. 62 over, we just found the mass of all of it together, 0.0619 plus 0.00175. And, that spits out something. Plus 0.00175. And we get our new density. And it's less than 1,000, so they float. And this is also something you're very familiar with. If you breathe in, you float. If you want to float on your back, you need air in your lungs. If you are on your back and you breathe out, you will sink. The human body is mostly water, plus a bunch of heavier stuff than water. So if you don't have a bunch of air in you, you don't have enough to cancel out those extra densities and yada, yada, yada. I honestly don't know the density of bone. Bone might float. It might sink. I actually have no idea. It's an interesting question that no one probably ever thinks about. Because bone is porous, but whatever. All right, great. I only have a few more things to kind of get through, and I'm going to try not to rush too much through them. So this first one is something you know. This is not a trick question. Yeah, way different answer. So the question is, some fluid is traveling in a pipe. What happens to the velocity when the pipe gets smaller? If you're like, how am I supposed to know this? If you've ever played with the water hose before, you know this. So does the fluid get faster, slower, or the same velocity? And think of your experience of playing with water hoses. If you've never played with the water hose, find someone around you that has watered some plants. All right, 10 more seconds. In 5, 4, 3, 2, 1. Ka-chow. All right, it gets faster. Again, you put your finger over the end of the hose, the water goes out faster. Now, why is this? This is because you can't squish a fluid. Fluids are incompressible. So something we're going to learn is that you got a certain amount of fluid going through here. I need the same amount of fluid to go through here. Why? If not, where the heck did my fluid go? If I have 5 liters of water that passes through here, I better get 5 liters of water that passes through here. Otherwise, where'd it go? Now, the only way I can fit that same amount of water through here in the same amount of time is by making it go faster. So that's how it works. Fluids can't be squished. So when you got this fluid getting to this junction, it's like, oh crap, we got to get through this thing. So you go faster to make it work, to get the same amount of fluid. Another example, this is like people coming into a classroom. If I have 10 students, say I have 50 students come into this classroom, I don't care how many entrances they come through. At the end, they all got to... So say you all come in through 5 different doors. Great, you don't need to go as quickly. But then at some point we all got to leave. And if there's only one door and we wanted to leave in the same amount of time, you'd have to go faster to make it through that. So, otherwise we're going to get jammed up and blocked off. And if this didn't happen, the amount of fluid that passes through something, the volume per second, is called the flow rate. The flow rate is how much flows. That's the rate of flow. How many liters every second? How much volume every second? That's flow rate. For now, don't worry about these second parts. In fact, I'm going to hide them. Don't worry about this. We'll look at this in a second. Don't worry about this. What I want you all to focus on is that flow rate is volume per second. How many liters per second? And this is a constant in a closed system. Flow rate is a constant, meaning if I have a big wide area and I have 5 liters per second, and then it shrinks to a thin area, it's still 5 liters per second. If I have it split into 2 different paths, the combination of those paths still needs to be 5 liters per second. That'd be like 50 students go in my room through one door, and then at the end of my class, 50 students go through one door and 50 students go through another door, and that doesn't make sense. Where do my other 50 students go from? So, this idea that what goes in must come out, or that things also need to speed up, this is going to be really important when you all get to physics 2, and you learn about current and electricity. Electricity, you can think about like water flowing through a pipe. And when a wire splits, the amount of electricity flowing through it will also split. Or if you have a single path, the amount of current going through it will be a constant, regardless if that path gets narrow or wide. Otherwise, you build it up and it doesn't make sense. So anyway, great. Now we can look at these other things. So we're going to look over here. Reminder to y'all, volume is area. We did this before. Volume is just area of something times, in this case, like the distance. If I take this area and I multiply by the distance, that's the volume. That's the definition of like getting the volume here. The area of some pipe times the velocity of fluid will equal the area of some other later point times the velocity of the fluid. Okay, cool. I think I should have time to be able to solve the remainder questions. So yeah, in a closed system, Q equals Q. Flow rate equals flow rate. If I'm going in, at some place I have 5 liters per second, some later place that's going to be 5 liters per second. Q equals AV, so the area times velocity of one equals the area times velocity of the other. If A goes up, V goes down. If A goes down, V goes up. You got to keep that constant. And that's why the hose works. It's got to go faster to keep the water flowing, to keep the flow rate constant. So, something that pretty much everyone knows, every kid that's played with a hose knows this, but now you know the reason. Fluids can't be compressed. Because they can't be compressed, it's got to go faster to make the same thing happen, to make the same amount of water pass through. And this is true of your human body as well. This next problem is, technically when pipes get really, really small, we run into some problems, but we're just going to ignore that for the next problem. Because your whole body is just filled with pipes called veins and arteries and capillaries. So this problem is probably not really accurate because the fluid dynamics I'm teaching you all, capillaries, they're so small, you run into some resistive effects where the walls of the capillaries slow stuff down, but whatever. Pretend like that doesn't happen. All right, so as blood passes through the capillary bed and organ, the capillaries rejoin together to form one big vein. If the blood speed increases by a factor of 4, and the total area of this vein, this venule, is 10 centimeters squared, what's the total cross-sectional area of all the capillaries together? So what are we solving for? We are solving for the area of all the capillaries. All of them. So let me actually rephrase this as a total cap. I'm not solving for the area of one capillary. I'm solving for the area of all of them. There's all these little tubes. And if you basically took them and you bundled them together as one big tube, what would be the area of that combo? All of them together. All of them in one big bunch. We can basically take them and imagine they're that. Take a bunch of small pipes, stick it together, ta-da, you made a big wide pipe. 4 times bigger. We also know the area of this vein is 10 centimeters squared. I'm going to go ahead and convert that to meters. Remember, I got to hop things twice as much as you might think you need to because it's squared. And then if you have areas and velocities, we're going to use the area and velocity equation I just showed you all. A1 V1 equals A2 V2. Just chuck them in there. Find it. So, the area of the vein, which is 0.001 times velocity vein, equals area 2 times velocity of capillaries. And then we're just going to take this and chuck it there. I got an equation with 2 unknowns. Well, I've got an equation. So we get 0.001 times 4 times velocity capillary equals A2 velocity capillary. Boom, they're gone. They cancel each other out. So long story short, area 2 is going to be 0.004. It's the long and short of this is if my blood speed's, if my fluid's getting faster by four times faster, my area is going to be 4 times smaller. So we can see that here. In the capillaries, my total area was 4 times bigger because it was 4 times smaller. or we can look at this. The vein has an area 1/4 that of all the capillaries together. Remember, this is not the area of one capillary. This is not the area of one capillary. It's all the capillaries together. The next question actually says, how many capillaries do you need to make this happen? That's the next question. So we basically took all these capillaries bundled together. How many do you need to make that happen? You find the area of one capillary and you divide this by that. So we took all our capillaries, all our little dinky things, and we basically pretended like they were one giant thing. Imagine I actually filled this entire thing with it. So this area is the 0.004. Each of these little dinkers is the area of one capillary. How many capillaries do you need? That's kind of the next question. So just to kind of quickly solve that. So I'd do 1,000 divided by 50 kilograms, and I'd find I need 20